Static friction between this wooden block and the table keeps the block from moving until it is pulled by a sufficiently large force. We'll use a spring scale to measure the force required to overcome the force of friction and move the block. In this case, the force is approximately 23 newtons. The force needed to slide the block along the table at a constant speed is less than 23 newtons. The coefficient of kinetic friction is lower than the coefficient of static friction.
Okay, now I'm going to explain what I want you to look for here. So, as she's pulling it and it's not moving, we know that we have static friction. And you see that needle is going to keep getting higher and higher. And the static friction matches her force until the box slides. And I want you to watch what happens to the needle once the box begins to slide. So focus on the needle. Increasing because we're in static friction. And then what happens? Needle jumps down and stays constant. So watch again. So static friction, static friction, static friction to a maximum value. And now we slide and it stays constant. Okay? So that shows us a relationship between static friction and kinetic friction. And that's what this graph shows us. This region here is the static friction region. On the x-axis is our applied force. On the y-axis is the force of friction. When there's no force applied, there's no friction. And then we start to apply a force and the object doesn't move. And we have a linear relationship. If we apply 1 newton of force, the static friction is 1, 2, 2, 3, 3. All the way up, in this case, to 23. Once we hit 23, in the case of the video, the box begins to slide. And then you saw the friction jump down. It jumped down to about 16. And then it stays constant. And no matter how hard she pulls it, this kinetic friction will remain constant. So I want you to realize the kinetic friction remains constant no matter how hard she pulls it, but also that the maximum static friction is greater than the kinetic friction. Okay, so the maximum, we reach the maximum, we start to move, and then the kinetic friction is less than the static. Yeah?
So is that like the same idea as like a car like burning out, like when they burn out their tires? Like the same idea?
Keep talking and explain what you mean.
Like you need a lot of horsepower to break the tires loose, and then once you get them going, then it's like you don't get any grip.
Yes, it's the same
Okay.
idea. Right. It's good. Don't do that. Okay, now I want to work through an example here or something. All right, so I have this friction box here, and in here I'm going to put 1 kilogram mass. And I want to draw the free body diagram for that box. All right, so we have the box. There's 1 kilogram in there, right? So it's about 9.8 newtons. So we're going to say that we're going to just round it to 10. So the force of gravity on that box is 10 newtons. We know that there will be a normal force up equivalent to that, 10 newtons. And now let's say I attach the scale to the box and I pull on it. Right? So I pull on it with a spring scale. And I take the reading off that spring scale, and the scale reads 5 newtons. The box is sliding at a constant velocity. I pull it so it slides at a constant velocity, and it requires 5 newtons of force to do that. So that means I have an arrow backwards, right? Because we're not accelerating. And since it's sliding, the type of friction present is what kind? Kinetic friction. So I'm going to write force of friction with a K here for kinetic. And what's its value? 5 newtons. And I know that because I measured the velocity, it was constant, we're in equilibrium, I was applying 5 newtons of force. So now I want to look at the ratio of the kinetic friction force to the normal force. I know it seems like a curious thing to do, but you'll see why. So I'm going to take the ratio of the friction force to the normal force, and it is 5 over 10, or 1 to 2. which in a decimal is 0.5. So I just did an experiment and I found out that the ratio of kinetic friction to normal force is 0.5 for that type of box on that type of desk, right? It's surface dependent. If I sprayed my desk with Teflon, then this friction would be much less, right? That's like a non-stick coating on your pots and pans. This might be 1, so then our ratio would be different. But for the setup we have now, the ratio is 0.5. Now I walk over and I put another kilogram in there. So now there's 2 kilograms in the box. So now gravity is pulling down harder on the box. It's pressing those surfaces together. So now my free body diagram would be, FG would be what? There's 2 kilograms in there now. Right, so let's call it 20. That means my normal force is 20. And now I grab my scale and I pull it at a constant velocity and I look at the scale, and the scale now reads 10 newtons. So it's moving at a constant velocity, so I know that there's a kinetic friction force again, and it has to be equal to 10 because I'm at equilibrium. So it's 10 newtons. And then I look at my ratio again. What is my ratio of kinetic friction to normal force? Friction force is 10, normal force is 20, or 1 to 2, which in decimal is 0.5. So I see again, same 2 surfaces, the ratio of kinetic friction to normal force is 0.5. And now I put another kilogram in my box, and gravity pulls down with even more force, and now that force of gravity goes to 30 newtons. And then I know that my normal force is 30 newtons. And then I wonder, I say, maybe I could predict how much force I need to move this at a constant velocity. How much force do I need? 15 newtons. Now how'd you get that? Because you know that the friction force and the ratio 0.5 related to the normal force that we know. So 0.5 of 30 is going to be 15. So let's look at that. The friction force over the normal force is 0.5, because we've measured that. So what we found out experimentally is that friction to normal for that box on that surface is 0.5. If my normal force is 30, then I can calculate my kinetic friction is going to be 15. And if it's 15, then that means I'm going to need to apply with my scale 15 newtons. So by doing an experiment, I was able to find that the friction to the normal force relationship is that the friction is 1/2 of the normal force for those 2 surfaces, and then I can apply that knowledge and make a prediction about how much force I would need to move it at a constant velocity. So that seems like it's probably a pretty important ratio. We could do a lot with it. And so we give it a name. The ratio of friction force, kinetic friction force to normal force, is called the coefficient of kinetic friction. And we give it a symbol. We give it a Greek letter, mu. Basically a U with a little tail on it. It's the Greek letter mu, it's lowercase. And because we were dealing with kinetic friction, we're going to put a subscript on there, K. So mu sub K is the coefficient of kinetic friction. It's found experimentally through these 2 experiments, for example, but then it's useful for calculating friction and other things as we move through the year. We'll be able to use it for other reasons. And in equation form, you can remember it as force of kinetic friction equals mu K times Fn.